So we have the n-type and the p-type. And n-type majority carriers are electrons and the minority carriers are holes, and we explained why. That we inject phosphorus. Phosphor has 5 electrons in their valence shell, therefore would have covalent bonds with 4 adjacent silicon atoms, and it would have 1 extra electron without creating an extra hole. So for every phosphor atom, you would have 1 extra electron, so the majority carrier would be electrons. And for the p-type, it would be the other way around. The majority carriers would be holes and minority would be electrons by injecting borons. The one thing that I wanted to note here is that right now the net charge in both of them is equal to 0. Why? Well, because in here we have silicon and phosphorus, and in silicon we have the same number of protons and electrons, and this also applies about the phosphorus. So the net charge in the n-type is 0, and so is the net charge in the p-type, which is 0 as well. Now imagine that we put these two n-type and p-type next to one another, and we want to see what would happen. So here would be the n-type. Let me just change my color. This would be the n-type, and this part would be the p-type. So in the n-type, we have the concentration of electrons is more than the p-type. So we would have the movement of electrons from the n-type to the p-type because of what we call as diffusion. I want to show you what this diffusion is by using of a simulation. Just imagine that we have some electrons and holes at both sides of this divider. And if I remove the divider, you see they would move to each other's side because of the because of the difference in their concentration. This is called the diffusion current. You could test this by putting 1 drop of ink in the glass of water. You would see that the ink would move. You would have a diffusion current until the ink concentration is the same throughout the whole glass of the liquid. So in here, one question that you might ask is that, are these really electrons and holes? Well, no, I just wanted to use an example because we know they also apply a force or on one another. I just imagine that we said these are electrons and holes without having the electric field. Only because of diffusion, we would have such a current, the diffusion current. But in here, let's see what would happen in our NP junction. So as the electrons move because of the diffusion to the p-type, the n-type would become a bit positive because obviously it is losing electrons. And holes, and well, the electrons would come to the p-type, so this side would be a bit negative, or the holes would move to the other side. But we know that right now that we have a net charge, we would have an electric field from the positive side to the negative. Let me change my color. So from the positive to the negative. Now, the current because of the electric field is the opposite of the diffusion current. Why? Because if before the electrons would move in this direction and holes would move in the other direction because of the diffusion, right now we know that the current caused by electric field is the opposite of that, meaning holes move in the direction of the electric field. Let me show it here. Holes move in the direction of the electric field, and electrons, we know they move in the opposite direction of the electric field. You see, we have a diffusion current which moves from here to here, from the n-type to the p-type, but this diffusion current would cause a net charge which causes an electric field, which that electric field would create a current which opposes the previous ones. In other words, we could say that the diffusion current would cause a net charge which would cause the creation of an electric field which opposes the diffusion. So this would go on until at one moment the diffusion current and the electric current are equal to one another. At that point, we wouldn't have any more current, and we say that the PN junction is at the equilibrium. In fact, even though I wanted to leave this as an exercise to you, that how would we calculate this E, the field at which, or the voltage at which the PN junction would be at the equilibrium. But I think it would be a good practice to try to actually do it ourselves in here because I want to show you something that how when you witness something or see something in the experiments, you would try to quantify that using the mathematics. So imagine you want to understand or quantify or calculate an equation for the diffusion current. So we say the diffusion would happen because of the difference in the concentration. In this case, the difference in the concentration of the electric charge, of the electron charge. So imagine that we have some electron or more concentration of electrons at one side than the other. Obviously, diffusion would say that these electrons would move to the other side. So we say the diffusion current density has a direct relation. You see, I say current density because I want to ignore the surface. You know, if you multiply the current density by A, you would get the current. But say the diffusion current density has a direct relation with the change in the charge of the electron, right? With respect to the X. Obviously, if the change is more, the diffusion current density would be more. So the proportionality constant, we would call it D, and for electrons, I call it D of N, and we call it the diffusivity. In other words, you could also say that diffusivity is a relation between the current density, the current density and the change in the concentration of the electric charge throughout the X. So if we have some amount of change in the concentration, what amount of current we would get? You could just imagine this in your head, that what a good, quantify or quantity this is. It is equivalent to maybe to the capacitor that we might introduce to you in the next lecture, that we say for C, we say if we apply for a capacitor for two plates, if we apply a voltage at both of its sides, if we apply a change in voltage at both of its sides, what current we would get? This ratio would be called as the capacitance. So in here, they are actually similar to one another. You could even say that from the second law of the of the three laws of physics, obviously, you would say that M is equal to F divided by D of V to D of T, meaning if we apply a force, how much that would change the state of motion, and we called it inertia. And also for the inductor as well. So in a way, they are also some representation, some kind of inertia if they're in their own meaning and concept, I guess. So if we apply a change of concentration of something, how much current or current density in this case you would get is the definition of the diffusivity. But how would this help us in calculating that E field? Well, we know that this is diffusivity of electrons. We obviously would have the current density for the holes as well. And then we have another current. That current is because of the electric field, and we know that that is calculated as NQ, the mobility, times E. In the previous lecture, we actually resulted that by saying that the V speed has a relation with the electric field, and the proportionality constant, we call it the mobility. If we multiply both sides by Q, which we defined before, this would be the current density, and obviously this side would be the current density as well. So we would have a current density for the holes and one for electrons. So we equate them to one another, because at the moment that they are equal to one another, then we would be at the equilibrium, and from there we calculate for E. You could just I guess resolve that yourself. Actually, I want to also give you another hint in case you get stuck. Just imagine we have some holes, some electrons and some holes in here, and you want to calculate the diffusion current. So this is the electrons and these are the holes. For the electrons, obviously they would move from one side to the other side, that we call it the diffusion of the electrons. For the holes also, we would have the same thing. We have the concentration more here than the other side, so holes would also move in here. But you know, the convention of current is that it is in the direction of holes or the opposite direction of the electrons, which means if holes move in this direction and electrons move in this direction as well, then the resulted current, the overall current, is the subtraction of them both. And you could also calculate this for our case that we have more electrons on one side than the other, and then go for the calculation of the equation. For the electric field, obviously it is equal, meaning if electrons move from one side to the other side, because of electric field, electrons would move from this side to this side, and holes would move from the left side to the right side. And obviously you could just calculate this, or and I guess in a more simplified version, you could just calculate for electrons, for the diffusion current for electrons and also the electric current for electrons, and equate them to one another, and you would get one electric field. That electric field that you get, that you solve for, would be the electric field that at the equilibrium of this PN junction that we also call a diode. In the next lecture, we want to abstract all of these things.